Hello, ladies and gentlemen, and welcome to today's event entitled Scale Out Computing Using R, Matlab, and Python with Microsoft Azure. To learn more about the ways you can participate in today's event, please click on the Q&A button in the lower left-hand corner of your screen. If you have any difficulties viewing the stream, please refresh your screen by pressing the Control F5 on your keyboard. I would like to turn today's event over to your presenter, Wenming Yi, Senior Research Program Manager. Wenming, you now have the floor.
Thank you, Stephanie. My name is Wenming Yi. I am a Senior Research Program Manager at Microsoft Research. Here at the bottom, you can find my Twitter alias if you'd like to follow me, and especially if you have further questions after the webcast. I'll be very happy to answer the questions that you may have. So today's topic is on scaling out on Windows Azure. So as many of you know, that cloud is scalable by design. We have multiple data centers, and we have many millions of machines in each of these data centers that are able to handle workloads at a global scale. And the ability to use the cloud at a scale is also a very desirable technical skill these days. Many companies are looking for developers and as well as users that are able to take advantage of compute at scale. The second part of the webinar here is to look at some of the options for technical computing at scale on Windows Azure, or Microsoft Azure, as we have just renamed it. Some of these options are for running executables that you compile yourself and you optimize, and that also includes Matlab, R, which are very popular for people who are doing technical computing or machine learning or any type of statistics work. We also have Python, which is an open source ecosystem. It's actually much more than just a programming language now. In fact, PyCon is actually happening in Montreal as we speak. So we'll look at some of these options for scaling out those compute. So it goes beyond simply your desktop, which is where the value comes in for cloud computing. And finally, I would like to introduce you to the Windows Azure for Research program that Microsoft Research is running. We have over 100 projects in progress right now. We're working with various academic institutions, trying to really bring the people together to innovate based on the fact that we now have the ability to do collaborative research in a common platform, which is Windows Azure. So the first thing I want to talk to you about is the global footprint that we have. So if you look at some of the blue dots here, those are the data centers that we have around the world. We have data centers in the U.S. There are 4 of them: North Central, South Central, East, and West. We also have 2 data centers in Europe and 1 in China, and we just opened up 2 in Japan as well. And there's another one in Hong Kong, which is relatively smaller. And then we have a very large data center in Singapore that serves that region of the world. Some of these data centers, as you can see, are extremely large, and they cover many football fields worth, and they are generally in the cost can range from hundreds of millions to billions of dollars for these data centers. They're usually located very close to electricity sources that are cheap. That also allows us to keep the cost down and pass that saving on to our customers, which many of them are internal, such as Bing and Office 365, and many of the other services that runs on Windows Azure continuously and every day. The first item we want to discuss here is the paradigms or the various offerings of cloud computing. This is important because these different computing paradigms target different users. And this is something that is very important when it comes to selecting what you want to actually use. IaaS is very popular. It's probably one of the most popular cloud computing, I would say, paradigm or platform. So the idea is that you simply um, uh, host a machine that is using a virtual hard drive. I just saw PowerPoint went out for a second, so now we're back. The idea is that you can take a virtual machine image and put it in the cloud, and you can also download that if you need to use that on your local machine. So this is really targeted towards IT administrators and sometimes developers and users, because you're simply hosting a machine in the cloud. This is more or less a server that you own and you administrate. So there's no additional things that you will have to learn to be able to use it very quickly. But the problem with that approach at scale is that you will have to have a virtual hard drive attached to each of the machines as you're deploying them. As you can see, it can become a fairly large task if you started building a cluster using many infrastructure as a service virtual machines. So you can essentially start to have hundreds of disks laying around. They all each have their own states. So the second paradigm here is the platform as a service, which is very much what Microsoft has invented. This is what we initially started to use. So the idea is that you have stateless machines, meaning that you don't save anything to your hard drive locally, even though we do have local hard drives. And what's really important here, they do scale. They scale very well, and a lot of the scalable services are built on top of platform as a service. We have services that are running that can go beyond thousands and even tens of thousands of machines by just simply clicking a button and deploy that. But unfortunately, that's mostly targeting developers. So you'll have to go into Visual Studio and run a lot of that yourself. So you have to build the software yourself, and a lot of the software as a service systems are built that way. So you do need the developer's skills to be able to do this. The third one is software as a service, which is very easy to use. This is something that someone has built for you, or a developer has built for you, and we have an example of that. It's mostly targeting domain users. So you're simply consuming a service, such as your email service, very simply put. And what's important here, it's targeted towards domain users. For people who are not developers, who are not IT administrators, software as a service is what you really want to do. Here are some of the example workloads that really need a cluster to be able to use. One of the most popular one is digital media rendering and encoding. And it turns out many of the supercomputing the capacity today are actually used for that. So there's a lot of CGI or computer-generated images or animations that are done that way. And financial and risk calculations, those are also very popular. That extends to Windows Azure as well. We have financial companies that have hundreds of thousands of cores they use each day to do risk calculations. And finally, engineering and modeling and simulation. This is a more traditional and HPC application where it may require some specialized hardware, such as InfiniBand, which I'm very happy to report that Windows Azure does now support InfiniBand and high compute instances. And finally, the computational life science, which I'm seeing a very large growth in the U.S., especially the funding agencies are starting to provide a lot more funds, or at least having a shift towards traditional science, towards computational life science, which demands a lot of computational power. And So let's take a look at some of the different scale out scenarios or applications that people have been using. So the first one is MPI. So this is the traditional HPC crowd. Essentially, you're running matrix solves at a large scale, solving ODEs, solving PDEs. Those type of applications requires InfiniBand or very low latency latency and high bandwidth interconnects. So Windows Azure does have that, and you have to use Windows HPC. We'll look at those software options in the second section of this webinar. The second scenario is embarrassingly parallel applications, which are essentially each of the compute units or each unit of work is independent of each other. And this is very much suitable for the cloud because cloud has hundreds of thousands or even millions of commodity machines that you can simply spin up and run applications. Since they don't necessarily, the generic instances don't necessarily have InfiniBand, you can simply spin the hundreds of them up and be able to scale linearly. So since they don't really have to communicate with each other very much. So we'll show some examples of that as we go forward. And also finally, there's this IO-intensive application, which are starting to become much more popular. There's the MapReduce paradigm. The idea is that you take your compute to where the data is. Essentially, a lot of these compute nodes have huge amounts of disk space and very fast access to the disks, and you're trying to build a virtual file system on top of it, such as the HDFS, and then it will do the partitioning for you automatically. So, and then you have a scheduler that sits on top that knows where the data is on each of the nodes and how they're partitioned, and would be able to schedule to have that code run on that machine. So we're not going to cover that because this is a different topic. But instead, we're going to focus on compute-intensive applications that includes many of the technical computing software. So I have a demo here, which shows you the Windows Azure in action. So this is a piece of software that we've written, or a software service that we've written, that sits on top of the platform as a service, which I explained earlier, meaning that the VMs are all stateless. So you don't keep any states on the virtual machines. That allows you to scale. So when you first deploy these applications to platform as a service, you would actually have a startup script which copies the necessary software onto each of the machines, and then you submit jobs to a global scheduler, and they're run in parallel. So here is the simulation. So one of the really important thing about the cloud is it's extremely reliable, and it takes care of all the patching, all the other things for you, so you don't have to worry about it. For example, my service here, which originally was intended to run for 2 days, turns out it has been running for 2 years because it's so easy for a lot of us to be able to demo, as well as you know, some of our attendees, like for conferences, like to just simply check it out. So the service has never been taken down. If any hardware has been broken, it will be swapped out for me automatically. If the operating system is out of date, it will be swapped out for me automatically. If there's any patches that needs to happen, it will do that automatically, and I don't have to worry about any of that. I simply focus on showing the demo and just, you know, having the service running reliably. So that is something that no one else was able to have before cloud was available. So we've run 2,300 simulations over the years, and we're simply running a very, you know, very small sample. And we're going to go to that URL right now. So it will take a few seconds for me to switch over. So just be patient and just watch the screen change over. And in the meantime, I will go ahead and go to the website and start that service. Hopefully, everyone should be able to see that website right now. So the website is done in such a way that we have some web front end. So you have a web front end. We also have some back end that does the actual computation. So the website should show up on your screen right now. So I have a gallery here which shows all the simulations that has been run in the past. And you would be able to look at the simulations that has run. We also have, oops. That's interesting. Looks like I have lost some connectivities here. And what I will do is I will go ahead and show you how Windows Azure works, and look at some of the different heat maps. So right now the website is running on Windows Azure, and let me show you where the cloud service is. So this is the Windows Azure portal, which is the back end of this particular service. So if I click on the service, it looks like the service has actually stopped for some reason. I can go ahead and start that again. Looks like that has been done by mistake. So the idea is that we have the dashboard, which allows you to look at what the cloud service looks like. So I actually went ahead and started the service again. So the configuration, and there's configuration, monitoring, and scale. So if I look at scale, you would be able to see that you can move a slider and increase the number of instances that you can have. So for this particular service, I have 3 different type of instances. As you can see, there's an instance count of 4. This is the actual compute services. So the compute services does the heavy lifting. It does the actual web forecast for you. And then there's web instances. As you can see, there's web instances, which is the front end. So I have 2 of them to allow the SLA to be really good at 99.95%. It doesn't really help if you turn off the service, so I'm actually redeploying it again. As you can see, there's 2 of them up front, and we also have some head node. We also have the head node that's running here. One of the hopefully it will take a few minutes for it to actually deploy if I have it stopped. So what we will do is we'll kind of go back to look at the slide, and then we'll come back to it, see if it actually deploys for us properly. The other interesting thing here is that I have a heat map which shows the CPUs are running at 99.9%, which simply says that the service has 4 jobs currently that are currently running. So we will have this deployed again and show it to you in a bit. So I'm going to go back to the slides, and perhaps we will be able to see some of the slides that I have recorded earlier, so that you have a feel of what it looks like. And once it's up again, we'll take a look at it again. So we're back to the slides. Yeah, great, thank you. So back to the slides. So here's what it actually looks like. There's the website, and there's the services that are running. So on the left-hand side, it shows all the simulations that has run over the last 2 years. And if I didn't accidentally just turn it off today, it would have been running for exactly 2 years and 3 months for a while. And the second piece is showing you the Bing map overlay of the actual forecast. Each of these forecasts run for about 8 hours, and once people have submitted them, they will be queued up and run in the back end. Let's take a look at the architecture real quick. So as you can see, there's a front end, which is just simply a website that are running. And then the back end, we have some compute worker nodes that are running the actual simulations. So the jobs are submitted through the forecast front end. and then they're submitted, they're run by each of the compute nodes, and they're usually on demand. And I can scale them up and down by simply moving a slider. And then there are almost, I think, 50 million objects that are currently stored in the Azure Blob Storage. That includes the images that are overlays, and so also some of the log files, and as well as the simulation results data that are post-processed for this. So the important aspect of this is that we built something that is using a platform as a service, which I simply deploy a package onto hundreds of machines, and without having to worry about the actual saving things to the disk. Let's just say I just turn it off, right? So if I want to turn it back on again, it will be exactly where it was. So just to give people a progress, we're actually deploying. It's copying all the files as we speak. The second interesting thing is that you can take we do have monitoring tools which allows you to see whether your CPUs are running. So in this particular instance, there are 12 cores running, and you're seeing that 98% CPU utilization. That simply means that you have all the instances running at full capacity. And you can simply, as I said, move a slider for the extra large instances to be able to run the compute. So we also have auto scale. So if there's a lot more demand coming in, if you allow that to happen, it will auto scale to multiple core, many more cores if needed. So here are the instances I showed you earlier. We have a head node which has two instances, and we also have a front end, which I have two web front end for people to be able to hit against in a round robin fashion. And then also, of course, we have in the back end, we have a compute service. Here's actually a heat map of 96 cores running. This is essentially 8 jobs that are actually 12 jobs that are running. So you're running a simultaneous simulations on 12 cities as we speak. And here's the actual what the portal looks like, which I would have showed you live, right? So there's the many cities that you're running simulations on. They will show you the progress that they're updating once every minute or two. And then this is the actual processing steps. So WRF by itself, which is the simulation code that happens, has to go through a workflow which does all the post-processing and pre-processing for it to happen. So in real world, there's really no easy, embarrassingly parallel application. A lot of times they involve post-processing and pre-processing that actually happens. So why cloud computing? That's actually a really good question. Many people that ask me. I have concluded that the abstraction for hardware and IT infrastructure is probably the #1 reason you want to do cloud computing. So for example, I have 3 large Cray desk site machines, which has 128 cores total. So I rarely use those machines anymore because the fact that I can simply go to the Windows Azure portal, click on a button, deploy a cluster, and it's running. So if you were to do that yourself, you have to first install the operating system, you have to tune it, you have to make sure everything's working, you have to install each of the machines, and then you have to install the software, and that's really a 1-week process if you want to deploy any type of applications. And centralized computing and data storage. So the idea is that if you have all the compute and data store in central location, you suddenly have the ability to give access to your collaborators, which is extremely convenient for any type of collaboration that you want to do. And finally, the always-on feature is really important. The fact that your service is always going to be running, unless you turn it off, of course. They will be guaranteed to work. Essentially, the downtime equals about maybe 2 or 3 hours per year. So the second piece I want to look at is the technical computing options, which are very important to many of our users here. One is that if you want to build something scalable, what are the things that you will have to do, right? So Visual Studio and Azure SDK, which you can use to build pretty much any type of scientific applications or business applications you like. So the way it would work is that you go to Visual Studio, you say File, New Project, you can add the type of roles you want. So it could be a web role as your front end, and then worker roles that are sitting in the back end. And then inside the worker roles, they can call Python, Matlab, or R through a system process. Essentially, you're doing pinvoke and to run these executables. This is very easy to do, and for most developers, they have no trouble. But in order to make something that is reliable and robust and has the web interface, it takes maybe days or even weeks worth of work. So there's a project that I recently started to build, which would be available to many of you. And if you are part of Azure for Research program, we will even help you to use it. But we're also trying to make a community so that I'm looking for people who would like to test it. So the idea is that for researchers, they're not developers. They don't necessarily want to write code, or they don't necessarily even have the time to be able to write code for in a month or maybe even weeks. So I think what we can do is we can actually consolidate a lot of the work that has been previously done. So I built the simulation runner so you can simply go to a web page, put your input file in a Dropbox, and run a parametric sweep application, which is very much suitable for the cloud. And we will pre-install things like Matlab, R, or Python. And we give you options of selecting different ones. So it gives you the flexibility of not having to learn a new system, as well as the ability to scale out your computation at a very clean way, or a very good practice using this piece of software. We will have some demos later in the process. So the second part, the third option is Windows HPC Server. So we actually have a commercial product which is called the HPC Pack, which you can install on Windows Server. So it's a very nice piece of software, but it's almost running like running Slurm or Load Leveler or any of those job scheduling tools, or running your own server farm. That requires you to know Windows Server sysadmin knowledge. So you have to be able to run a cluster and have to understand domain controllers and a lot of these Windows Server administration. It's not difficult, but it's not necessarily something that one researcher would want to do, which is to do administration and all of that. And the other interesting thing you can do with the Windows HPC Server Burst is that you can install the Matlab Compute Server, cluster server. So the way it would work, which I saw a question in the audience, is you would connect. You will install the software on Windows HPC Server, and the individual nodes would do a dial in or call in into the Matlab license server on the internet. And we'll have some screenshots of that in a later part of this. And the third part is actually the fourth one is the Linux cluster. So this is IaaS. So the idea is sorry, I got disconnected for just 1 second. I apologize. So we were just talking about Linux clusters. So the idea that Linux clusters would work is that you can simply deploy a Linux cluster however you like. These could be images that we create for you, or these could be images that you have yourself, or you can simply build them one by one. So you can do them by hand, or you can deploy them through a script. So I actually do have a demo of that, and you can find that in a hands-on lab of the Windows Azure training site. And the idea is that you would be able to run all of that through a script, create a cluster, but you will have to do administration on your own Linux clusters. And currently, we only support Linux as an IaaS option, which means all these Linux machines that you created will have to have an attached disks to them. And finally, we have support for multiple languages. So that includes Fortran and Node.js, .NET, Java, PHP. So all of these languages are supported. So pretty much anything that runs on Windows is supported. So the other thing I want to do here is to actually look at the generic implementation of a scalable solution, so which is the simulation runner. So many of you would probably be using it for some of your work, especially for the Azure for Research program. So while we're at this, maybe so I am loading the desktop as we speak. It will take probably just a few minutes. Ah, great. So as you saw at the very beginning of the presentation, I accidentally turned off a cloud service, which has probably 100 cores deployed. And as we're simply speaking, I just had to press a button and redeploy it, and it's all up and running as we speak. So this is absolutely the best platform you could possibly have when it comes to running compute. And think about the complexity of this if I were to do that myself, right? So if I accidentally did something to a cluster that I've built, and now I would actually have to do all kinds of troubleshooting. And instead, what I have done is that I've been talking to you through the slides, and the Windows Azure has been doing work in the back end for me. So the service is back up, and you can see in the gallery, it shows the simulations that has been run in the past. You can also look at the processing queues. So you can see that some of them are being downloaded, and some of them are being computed. So this is a live service that everyone has access to. So it really shows you the power of software as a service. And I can submit a computation if I need to. So I can simply go to perhaps, let's just say we'll pick San Diego here. How about somewhere warm? We'll just put somewhere warm here. We'll just put somewhere where I want to have vacation. There you go. So I can go ahead and save that. In 8 hours, it will have a simulation done for me. So this is the power of software service. So that brings us to talk about the simulation runner. The simulation runner is a work in progress, but it has gotten to a point where it's stable enough that I'm ready to look for some testers if you're part of the Windows Azure program. And you're also welcome to use it in the next 2 weeks once we have it, once we make it public. So here's something interesting here, which is the simulation runner allows you to simply go deploy a cluster by setting some of the environmental settings. So the way we've envisioned it is to allow you to go to a web page and simply say, here's my Windows Azure credential, and I want to go ahead and deploy a cluster with any of these installed. So what I've included here is the Canopy, Python, just a generic Python. Canopy is something that is done by a company called InThought. So it's a 64-bit version. So it includes all the machine learning packages, all the scientific computational packages that's there. And there's another company called Continuum, which includes the Anaconda software. So that also includes many of the software that you want, or software packages that you want. So you can simply click these packages and say save, and it will deploy them onto your cluster. And we also included Matlab runtime from 8.0 through 8.2, as well as R. So this, once you have deployed it, you're going to see that you're going to have a little cluster. And you can also scale. So this particular setup has the ability to scale to as large as if your account is. I currently have 9 nodes running. You can scale to 100 or even 320, which is the limit of this particular account if you want. So you can also, when you deploy, you can also choose between small instances, which have 1 core, as well as to up to 8 core instances, which is extra large. So you will have to make sure that your application scales at a thread level if you do use the large cores. And we will allow you to do core-based scheduling as well later. So let's actually look at some of these code that I run earlier. As you can see, I'm doing some testing on the system here. So this is actually a BLAST run. So as many of you know, that BLAST is a genomics code which allows you to search for certain features through a database, right? So it has a 4 GB database that you have to download, and it has an executable that you run, and then the results are simply the results that you're going to see if there is a match or not. So you can click through the matches, and you will see that in this particular one, there are some matches that actually occurred in the sequence that you gave to the program, which is BLASTX. That you run. To submit a job, it's actually pretty simple as well. So here you can select from local files, and you can select them from Dropbox. This is actually a feature that people ask me because people don't want to deal with lots of files. If I have a package that has, let's just say, 15 files, it's just a directory, executables and support files, you can simply put them in a Dropbox, and it will pick it up. And put them in each of the nodes to run. You can also pick them up from Azure Blob Storage. You can upload them locally, which has to be a zip file. And then you can run your parameter sweep application and just simply submit the job or save it. So you can also resubmit jobs if they fail, right? So here's a job that I see that ran very well. I can simply click on resubmit, and it has all the different options as well as things that has been filled out for you. So apparently this is actually from Dropbox. You can see the structure it read from the Dropbox and allows you to be able to do the running here. So that's a demo of this piece of software. If you would like to try it out or use it, please do drop me a line or send me an email to me or tweet me. So either way, it would be great. So we'd love to get your ideas or any new ideas that we can do. We'll also make it open source so that you can use it yourself. The nice thing about it is that it's simple, and it uses platform as a service at scale, which means you don't have to write any software to be run your scientific code. So we support R, Python, Matlab, any executables that you want to do, or PowerShell, even Ruby if you wanted to run that. So let me switch back to the presentation again. So as we're waiting for the presentation to show up here again, there you go. So the nice thing about the simulation runner is that I will be able to help you with a lot of it if you, and also I would be able to add features if you would like to have that. So just a quick review of what it looks like. So this is the Dropbox. You simply take all your stuff into Dropbox, and it will be picked up, and it will just run whatever you specify in the simulation runner. So as you can see, that these are the what it looks like. So creating a Linux cluster. So this is something that you can find on the Azure training content, which is listed at the back of this presentation, the resource section. The virtual machines for Windows Azure does support Linux. We have different flavors of Linux, and they're always updated. Our partners are very keen on working with us to make sure that they're up to date. If there's any security problems they have, it will be fixed, it will be patched. So these are all supported distributions. You can also upload your own. So you can create a VHD and upload that to be used on Windows Azure. There are tools that allows you to convert VMware images onto VHD, and then you can upload them onto Windows Azure. So it's pretty straightforward. And as I was telling you guys earlier, I have scripts that can deploy clusters of them. So it's simply using the Python SDK to spin up instances. So in this particular example here, is that if you go to the training kit, it goes through step by step, shows you exactly how to deploy it. So I'm simply using the IPython notebook, which connects to the IP engine or the IPython compute engine in the back end, and have a small cluster to be able to run a Monte Carlo simulation. So there are many ways for you to run embarrassingly parallel applications, and we also support multiple platforms. The only downside to Linux cluster is that you have to roll your own, and you probably have to secure them yourself. The other important thing about it is that they have to each carry a disk. So if you have 25 machines, you have 25 disks that are sitting in your blob storage, and you probably have to maintain. But if you just use a script to deploy them, you may simply say, okay, I don't really care about these disks. I'll destroy them and I will, redeploy them again. But they have to have the disks when you deploy them. But it's certainly an option if you have to have Linux, be able to use Linux. So here are some other links to how to use Windows Azure command line tools. So there's command line tools that allows you to copy files, deploy VMs, look at your subscription, automate a lot of the creation processes. This is where you want to go. So go to the windowsazure.com and search for CLI tool. So the CLI tool is written in Node.js, and it's usable on all platforms. So another option I want to talk to you about is Windows HPC Server. So Windows HPC Server is really about IaaS, which requires administration. So the idea is that you create a head node in the cloud by your system admin. So he'll create an AD, he'll create all these different things. It takes maybe 2 or 3 hours to do. So for example, the software as a service options, you simply deploy it and you don't have to worry about it. But here you're actually installing a server. You have to learn how to do administration on Windows Server, which is really fun. It's definitely worth doing once at least in your lifetime and learn how it works. But probably not for a researcher that would want to administrate a large Windows cluster. And then the stateless nodes, those compute nodes are platform as a service that allows you to be able to scale. So it is an option for people who want to be able to do, who have some sysadmin knowledge, but want a very robust solution that is supported by Microsoft to be able to run embarrassing parallel applications. So we do have commercial customers that use this, but they do have sysadmins that takes care of their cluster. Here's some, let's see, animation. Here's an animation of how it works. So the Windows HPC Server, you can also take that head node and leave it on premise. So you can do that as well. It's very flexible. But it's the same problem. You have to know how to do administration on a Windows server. Then there's you are allowed to add nodes that are local machines. So for example, there's actually companies that run this on their desktops, and you can also add Windows servers, which supports InfiniBand, and then you can add Windows Azure nodes, so this is the platform as a service nodes that you can add to it. We also support HPC SKUs now. So this has to be done through the HPC server. We support 120 gigabytes of RAM, QDR, which is 40 gigabps InfiniBand. So this is my understanding. It's only available in the Amsterdam data center, and I think it's becoming available in the Chicago data center as well. We have probably thousands of these machines that you would be able to access and run real HPC applications if you needed to. So it supports MPI, supports all the things that you will need for complex scheduling. So if you want to do that, which is traditional HPC type of work, please use Windows HPC Server. It works. Here's some screenshots. So if you want to create a node, you simply right-click and say, I want to add some Azure nodes. Make it 100. Make it 1,000,000. Here's what a job submission looks like. As you can see, it's very similar to the simulation runner, which I simply copied some of the interface from HPC Server. So the difference is, again, it's user versus sysadmin target audience, right? So you can essentially run your jobs. You can see the jobs submitting. This is actually a Matlab job. We're running some Matlab runtime work on here. And so here's another simulation that we did. So this is something called Modus Azure. We did some very compute-intensive work using the HPC server in the cloud to process Modus satellite data. And that takes years. That essentially, if you were to do that on desktop, it would take you, I remember it was 30 years or even more. So we were able to do that in the cloud by scaling out to hundreds of nodes. And obviously, that didn't take a long time. It take maybe, I would say, a month or so for the computation to complete rather than 30 years. And the cost is also becoming much cheaper. So these are some of the older numbers. Right now, the compute service has gotten a 35% off, and also the storage service is now 65% off. I think you can store a gigabyte per month is at 2 cents, 3 cents, 2 cents, I think it was. And the compute instances are 4 cents, I believe. You can get that done. So here's a preview of what Matlab cluster installation looks like. So you can install Matlab. So it's not a problem on Windows HPC Server. And they would actually have the licensing all done for you. So in fact, you can see that I ran through the cluster configuration and it finished just fine. So you have the, so you install HPC Server, you install the Matlab compute cluster, and it would just run. But there's a minor issue. You have to install VPN. So those are still things that we're figuring out for you, and we will have a more detailed write-up for you later on. So for the future IFPs, I would encourage you guys to look at, if you're using Matlab, please do, and we'll be very happy to help you to get that working on Windows Azure. That brings me to number 3, which is let us help you to scale your research. So we have some training schedules. We've been running almost 100 trainings worldwide by now. Maybe not that many, but we do have also the content available. It's 200 megabyte download, which shows you a lot of things that I showed you today. And also, you can apply for the Windows Azure for Research RFP program, which I will go into in detail as well. And also use Windows Azure to, and you can get help through our support program. So this is the Azure for Research program, and you can go to Azure for Research, which is the URL here, and you'll find on the main page, you'll find that this is the actual proposal that you have to fill out. As you can see, it's really not many things you have to do. So you fill this out, your institution, which university you're from, and also you need to write a 2-page proposal about what you would like to do on Windows Azure. It will be a free gift to your university and includes almost 500,000, more than that actually, more than 500,000 compute hours. So if you like to take advantage of the program. We will also help you to use some of our programs as well as help you look at some of the design. The Windows Azure program is really about bringing people together, and that's really the definition of innovation. When you bring people together onto a compute platform together, I think this is where we can really scale, not just simply for the computation you're doing, but also the knowledge that you'll have, as well as the innovation that we can have. So here are some URLs that are very interesting. So windowsazure.com, this is constantly being refreshed. There's a team of writers that does a fantastic job of keeping things up to date. We also have the Windows Azure for Research website, which you can go to. You can look at training schedules, you can look at technical papers, and you can also ask questions if you wanted to. So this is actually a URL for technical papers. So it goes into details of a lot more. So such as big data, such as how do you use the Windows Azure storage, how do you use compute. So these papers will continuously be updated, and you should go there for your technical resources. We also have an online training. This is a very light version of our hands-on training, which is 2 days. So this is probably takes you an hour to look through these videos, and they're done by Peter Wang, who is a fantastic developer for scientific applications and a founder of Continuum. And finally, we have a LinkedIn group which you can join, and also here's my Twitter, which you can follow. And if you need to ask questions, that's probably the easiest way to reach to me. And finally, there's a few more URLs that you can look at, and we'll make this deck available to you. Any questions? I see there is one. So I'll read it out. So when using the simulation runner, how do you install custom libraries which requires compilation, such as Python modules and involve C extension or simulation instances? So that can be done through Dropbox. You simply drop your compiled code into Dropbox, and it will probably be in the bin directory, and you specify, and it will just work. So we're trying to make this as easy as possible, and you can also use SkyDrive. We haven't built the support yet, but you can also just zip up your code and say upload and distribute, and it will distribute it onto each of the nodes. So that's something that we saw as a pain point for the users, and we're trying to make it really simple for you. And the other questions?
There is one more question. I'm going to submit that to you.
Fantastic. Thank you, Stephanie. So the simulation runner project package is currently not yet available for download, but we'll make it available very soon. And so you should probably ping me in, I would say, in 8 days. So by Friday of next week, we should have it up and running. And if you have something specifically you want to run or test, we would love to get the specific program you want to run, and we can test it for you. So you can send me a tweet, and I will be happy to work with you offline to do this. And what we really want to do is to make this part of a community and make it really simple for all of our researchers, because there really aren't any good free web-based scheduling tools out there. So this would make things so much easier, and to make it better, it requires a community effort. So please do send me emails, and it's actually running right now at simulationrunner.cloudapp.net. You can play with it. It's very, very rough shape at the moment, but we'll make it work. I've already tested on Python. I've tested on Matlab. I've tested on complex simulations like the BLAST, which is non-trivial because you have to copy a lot of database files over. I've also tested it for some other programs that I cross-compiled. And MPI does not work across many nodes, but it works on a single node. I did test that earlier. So you just simply package up MPI onto it, and you just run MPI using in each individual nodes. So I think that concludes our webcast. And if you have any further questions, please send me a tweet if you like, and I'll be very happy to work with you. And I look forward to your submissions for the RFP program for the next deadline, which is April 15th. And I apologize, it coincides with the tax day. And once again, I'll hand it back to you, Stephanie. Thanks everyone for attending.
Okay, great. I have enabled our feedback survey for this webcast. It should be opening in a pop-up window on your screen. The scores are on a scale of 5 to 1, with 5 being the highest. We would sure appreciate your feedback prior to logging out. You'll be able to access a replay of this webcast via a link that will be distributed via email post-session. I'd like to extend a big thank you to our presenter, Wenming Yi. This concludes today's webcast. You may now disconnect from this call.